Welcome to our tutorial on digital electronics, and in this tutorial we're just going to discuss about the asynchronous, yeah, that's right, asynchronous mod counters. Okay, so there you go. Yeah, that's right, that's counter. Okay, so in this tutorial, as I've just said, that I will discuss about the asynchronous mod counters. So here the counters that we'll just discuss about will just operate in the asynchronous mode. So imagine, or rather, just if you would remember from our previous tutorial on counters, if any counter just counts from 0 to, let's say, the state 3, it will just pass through the binary stages, 0, 0, 0, 0, 0, 1, 0, 1, 0, and finally 0, 1, 1. So basically a counter that counts from 0 to up to state 3, then it just passes through 1, 2, 3, 4. So it just passes through 4 states in total. Okay, so now each of these stages that you can see here, so each of these stages is referred to, okay, so I'll just write it down here. So each stage or count over here is referred to as a modulus. Okay, so this term modulus is just expressed here in short. So here mod counters refers to the counters, okay, that passes through all these stages. Well, you might be wondering as to why I did that, because every counter should pass through this stage. Okay, no problem, I'll just explain why. I'll just explain the reason. So basically what happens is that there are basically two types of mod counters actually. So the one that can count, okay, so I'll just write it down over here. So there are two types of mod counters. So one type of mod counter is just known as a full mod counter. Okay, so let's say if we just talk about a let's say a mod 4 counter, then this means that the counter can pass through 4 stages. Okay, so this is basically here this counter that can count from the state 0 to state 3 is basically a, or rather I'll just write down over here, so this is basically a mod 4 counter. Okay, so there you go. So the mod 4 counter actually passes through 4 stages, as you can see here. So that's the total number of stages it can pass through. So whenever a particular counter that passes through all of its stages, okay, that is just permissible under its under its ability, so that sort of counter is just called a full mod counter. So if you're just taking an example of mod 4 counter which just passes through all of the 4 states that is capable of passing, okay, then it's just referred to as a full mod counter. Okay, so it happens in many applications that we have to limit the number of stages that a counter should count. So in that case we'll just call them as variable mod counters. So a counter, okay, so if we just again take the example of a mod 4 counter in this case, so here the mod 4 counter can count up to a maximum of 4 states. So if we just design this counter in a way so that it can count up to 2 states, so we're not utilizing all the 4 stages that it's capable of counting up to, so we're just using a part of it. So here we can change the maximum limit up to which, or rather the maximum number of stages up to which a counter can count. Okay, so if that we just execute in this case, so that at that time the counter, it will be referred to as a variable mod counter. So variable mod counters refer to those counters in which the maximum number of states that it can just count up to is just limited by some external logic circuitry. Okay, so having that said, okay, we can we're just going to discuss here about the functioning of the asynchronous mod counters, okay, with the example of a mod 6 asynchronous counter. All right, so we're just gonna discuss about the functioning of the counters, the asynchronous mod counters with the example of this mod 6 counters. So but from the name over here, you can understand that this counter should pass through 6 stages, including the 0 stage. So it just will pass through the stage from 0 to stage 5. Okay, so therefore in this mod 6 counters, it's also quite important before we draw the circuit to determine how many number of flip-flops we'd be using. So in order to do that, we have a way of calculating that out. So we'll use the relationship n less than equals to 2 to the power n. Okay, so For a counter that can count up to, let's say, n states, it's just referred to as a mod n counter. Basically, I mean, speaking from the general point of view. So here, the maximum number of stages that the mod n, I mean, an n small n bit counter can count up to is just given by 2 to the power n. Okay, so here n represents the number of flip-flops, so we'll just pen it down over here. So here in this relationship that I've shown you here, n represents the number of bits, okay, and capital N represents the number of states that the counter should pass through. So if we are just planning to construct a mod 6 counter, so then if we just put the capital N, that's the number of states till 6, then the equation looks something like this: 6 less than equals to 2 to the power n. And now the small n representing the number of bits present in the counter circuit, it actually gives us the number of flip-flops need to be used, as a single flip-flop can store up to 1 bit of binary data. So just having this sort of calculation, if we just apply log on both sides and calculate the value of n, then it would be something like this: n minus 1 equals to log 3 by log 2. You can just try this out yourself. It's just 9th grade mathematics as such. So if we just calculate the value of n, we'll get n as greater than or equals to 2.584 and so on. So here the number of flip-flops can never be a fraction, so therefore, as the equation states, that n must be greater than or equal to 2.54, I mean 2.584, or rather 2.6 if you just round this up. So then we're just taking the minimum number of n as equal to 3, which is of course greater than the figure given here. So therefore we are just going to utilize 3 flip-flops in order to construct a mod 6 counter. So enter the circuit of a mod 6 counter. So therefore we have that's too small in shape, or rather in size. That's 1, okay, that's 2, all right, and there's 3 flip-flops. So here we're going to utilize basically T flip-flops, okay, to construct the circuit of a mod 6 counter. So this is basically T1, okay, T2 and T3. So these are basically the T inputs of the T flip-flops. Okay, so now the T inputs of all the flip-flops are kept at logic level 1, okay, and now here we have their clock inputs, okay, with the bubble given at the beginning of the clock terminals. We can get to understand that all of them are negative edge triggered T flip-flops. Okay, so there you go. So here are the outputs, basically Q2, Q2 bar, Q3, Q3 bar, and Q1, Q1 bar. So here we apply the actual clock signal to the input of the first flip-flop, okay, while the output of the first flip-flop, that's the Q output of the first flip-flop, drives the clock of the flip-flop 2, and then the Q output of the second flip-flop drives the clock of flip-flop 3. So there you go, that's the circuit, and we'd obtain the outputs right from the Q terminals. So apart from that, we'll have this clear, okay, so or rather clear bar inputs on all the flip-flops connected to the output of a NAND gate. Okay, so there it goes, we have this connected to the output of a NAND gate, and the input to this NAND gate is just obtained from Q2 and Q3. So there you go, that's basically the circuit of the mod 6 asynchronous counter using T flip-flops. So let's just go through the truth table of the T flip-flop once again. Okay, so with the clock signal on, okay, so which are of course negative edge triggered T flip-flops over here, if we just keep the T input at logic 1 level and assume that the previous stage of the output is something like this, then whenever the T terminal is kept at logic 1 level, the outputs would just toggle, and if it's kept at the logic 0 level, then the output would not change its state at all. So that's here we have the truth table of the T flip-flops. So there you go, that's the T flip-flop truth table. Right, so just keeping that in mind, and just a little recapitulation about the T flip-flops, we'll just go into the circuit of, or rather how this this counter functions. Okay, so here let me take the red color, okay, and I'll just give you the states, or rather just write them down over here. So here are the states, that's Q3, Q2 and Q1, and this is the R. So R is actually the output from this NAND gate, as you can see over here. So having the clock inputs on each of the flip-flops, basically, or rather at the input of flip-flop 1 respectively. So if we just assume that all of them, or rather all the flip-flops, okay, has their output, okay, set at logic level 0, so there will be, all of them will be at the 0 0 0 logic level, so their outputs would just be 0 0 0 in the beginning. Okay, so now if we just assume the arrival of the first clock pulse, then on the negative edge of the first clock pulse, what would happen is that the output would just change to logic level 1 upon the arrival of the first clock pulse. Okay, so the output of this flip-flop 1 would just go or rather just revert from logic level 1 to logic level 0 to logic level 1, while the outputs of flip-flop 2 and 3 remain at the logic level 0, since they do not encounter any sort of negative edge of any pulse. So therefore now the output of Q1 being at the logic level 1, whenever it meets the on the negative edge of the second clock pulse, then the output of Q1 would just change to 0. Okay, and now Q2 sensing the falling edge of this output of Q1, it just moves from this state. Basically it just moves from, its output just changes from 0, logic level 0 to logic level 1, while the output of Q3 still remains 0, as it hasn't sensed any sort of negative edge at all. So this way the count just moves on from here. If you just take a look over here, this basically represents the 0th state. This is the first state, that's state number 2, that's second state, and the count just moves on this way. So here flip-flop 1 represents the LSB of the binary digits being generated as the count of this circuit, and here flip-flop 3 would represent their MSB. So the count just moves on through all these states, and slowly it would go to the stage 5, that is. Okay, so here is stage 5, which would have, or rather we would get an output of 101 at the stage 5. Okay, so now getting the negative edge of another clock pulse at the stage 5, what we have is that the outputs of the flip-flops would just, okay, so let's just assume that there are, all of the the output of this counter is at the the state 5, so it has the output of 101. So upon arrival of the next clock pulse, the negative edge of the next clock pulse, what happens is that the outputs of this counter just moves on to the state 110. Okay, so here since the clock comes and the output of flip-flop 1 toggles from logic level 1 to 0, the clock 2's flip-flop, the clock 2, the clock of flip-flop 2 basically senses this falling edge of the output of flip-flop 1, and it just moves from the logic level 0 to logic level 1, while the output of flip-flop 3 remains the same, as it doesn't sense any kind of negative edge of the output of Q2. So therefore this state 110 remains for a very brief interval. Okay, so this state 110 remains for a very brief interval. Okay, and then what happens is that whenever this state occurs, so it's an invalid state, okay, according to the stages that the counter should pass through. So if we just take note of this NAND gate, which has its input connected to the Q2 and Q3 of the outputs of the flip-flops 2 and 3 respectively, so at that time the logic level 1 signals just travel to the input of this NAND gate, so that the output R is a 0. So now this 0 is just fed to the clear inputs to each of the flip-flops, okay, simultaneously, and their outputs just move on to the logic levels 0 0 0 again. So we can see over here from this stage on the output of R being a 0, okay, which was at the level 1 throughout. So here the output R being at the logic level 0, the flip-flops just go back to their 0th state, having the output output Q3, Q2, Q1 as 0 0 0 respectively. So this is basically the way, or rather the mechanism, in which we just limit the counter up to 6 states basically. So that's why it's called a mod 6 counter. So if we just try and draw a clock, or rather a timing diagram in order to depict this operation. Okay, so there it goes. Yep, that's right. So here is the clock input, that's Q1, Q2, and here's Q3, and these are all the time axes in each case. So if you just take a note of the clock pulses that keeps coming at regular intervals of time, then on the negative edge of each clock pulse, what happens is that the output of Q1 just switches back to logic 1 level and just falls down again upon the arrival of the negative edge of the next next immediate clock pulse. So whenever the output of Q1 falls down, the output of Q2 goes up and continues till it encounters another negative edge from the falling pulse of the falling output of the Q1. Okay, so this phenomena just goes on, and finally Q3 would go up when it encounters the negative falling edge of Q2. So this would just go on continuously. Okay, so here, as you can see, the counter just moves to the state 0 0 0 over here, where none of the outputs of the flip-flops are at logic level 1. Then it just moves on to the 0 0 1 state, and then again it would just go on to 0 1 0, finally to 0 1 1, and then to 1 0 0, and just this count keeps on going till it reaches the stage 5 over here. So that's basically what we had to discuss about the operation of the mod 6 counter using T flip-flops. So I hope you've understood about the way that the counter functions. So just see you in the next tutorial on digital electronics. So till then, it's just thank you for now and goodbye.